All right, we're live, and we're back. Hell yeah. Um, I've been out for a while. I've been what you call it? I went to New York to try to get some like paperwork done on my passport, and we're back. And not only are we back, we're also gonna do solid phase. Also gonna study solid phase peptide synthesis because yesterday I was in the lab, and then I asked my postdoc a question like, "Sir, oh kind sir, what does the pre-activation do for the solid phase peptide synthesis?" And then like, bro, I mean, I kind of felt embarrassing, but low key, like the way for you to learn is to get embarrassed by not knowing, and then you just then seek out the knowledge, right? Well, you don't have to be embarrassed, but either way, I felt embarrassed. But point is, it's a part of the journey, and yeah, I am. But it turns out I have so many implicit assumptions on solid phase peptide synthesis, right? Because from my understanding, right, solid phase synthesis is basically how you grow how you make a peptide by anchoring it onto a resin, right? So you think of your resin as like some structure, some like polymer, right? Something like this. You're growing you're growing your peptide. Add stuff, keep on adding stuff, like Lego bricks. And of course, like there are nuances to it, like right, like a lot of times so for instance, the residues you will be attaching may or may not have like reactive sites on them. For instance, histidine, right, like has a reactive nitrogen, and a lot of times those reactive sites will be blocked off by other groups. So if you ever like done solid phase peptide synthesis, you might see like the bottle labeled like F-mark histidine, which obviously covers like the amine and the carboxylate groups, right? No, the carboxylate groups, right? Then in parentheses TRT, tridol, which is like trichloro something. I can't remember what it is. I think tridol is like 3 rings, 3 cyclohexene rings. I think they're benzene rings, 3 cyclohexene rings. Either way, we'll check it, right? So yeah, there's that, and somehow I forgot what pre-activation does anyway. Yeah, anyway, the point is, like, before I go to work, I must know what pre-activation is. So let's see. Hold on, where's my camera? This way. Yeah, alright. Let's look at HCTU pre-activation. Oh, shout out Epidemic Sound for like this free shit. Alright. Pre-activation in SPPS. No, I did not mean this. SPPS test for successful handout. Pre-activation of incoming amino acids can help eliminate guanidination as a coupling agents are consumed, minimizing side reactions during amide formation using pre-activation. 2021. Oh, this is a whoa. I mean, we can kind of skim through that. Like 2023, development of a mechanistic amino acid activation. Like it's not even complete. Improving to chlorotrityl chloride resin activation. Overcoming aggregation. Alright. Universal photosynthesis via solid phase methods. 2025. You know what? I might just go here. Please. Actually, okay. Let's see. This is Loki, the brand we are using. This guy. We have this guy. This guy is awesome. Not what I'm using right now. Well, obviously, like I'm not gonna talk about it unless like it's been shown without me knowing. But this guy, amazing. Okay, that's just basically product placement. How does peer activation in SPS work? Part of me is thinking I should watch a YouTube video. Solid peptide synthesis for beginners. All right. American Peptide Society. How long have they been in existence for? Anyway, that's not the point. The point is, we want to know peptide synthesis and we want to know pre-activation, right? So if this is your first time synthesizing a peptide on solid phase, you do not have access to all that. Oh, and you don't have access to this, you need to do the following. Blah, 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 blah. Alternative manual peptide synthesis setup. Blah, blah, yada, 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 yada. Okay, but I need to find the whys, though. Whys. Why are we doing stuff? I'm clicking on this guy because it said explained, right? Reject all, because why? Solid phase peptide synthesis is a method used to create peptides by assembling amino acids in a stepwise fashion on a solid support, such as a resin. Okay, cool. This process allows peptides to be synthesized in a controlled, efficient, and scalable manner. SPPS simplifies the purification process as the peptide remains attached to the solid phase throughout synthesis, making it easier to remove byproducts and non-functional peptides. So, part of what my postdoc was telling me yesterday was that during the cleavage of the peptide from the resin, we do what we call global deprotection, where we basically remove all the protecting groups on all the reactive species, plus the resin itself, plus the I don't think we don't remove the amide cap. We don't remove the amide cap. We just remove the resin. But either way, let's continue reading. It can be defined as a process in which a peptide anchored by its C terminus to an insoluble polymer is assembled by the successive addition of protected amino acids. Protected, yeah. So remember when I said that histidine, for example, has a trityl to protect like the reactive species on it? Yes. I mean, also like they all have like protective species on all like the reactive parts anyway. So like your carboxylates and your amines will have like NH2L or will have like FMOP or some other like group on it. Okay, so each amino acid addition is referred to as a cycle consisting of cleavage of the N-alpha protecting group, washing steps, coupling of a protected amino acid, washing step. Alright, so cleave, wash, coupling, wash. Right, so we cleave, basically we expose. Let's actually think about this, right? Because like, let's actually, let's go ahead. Let's actually think about this, right? Because like, say this is your resin, right? This is your resin. This is your solid resin, and then what they're essentially saying is that the C gets attached, right? So, if you're synthesizing a okay, I don't think it's here. But anyway, so let's say this is our resin, right? Trust me, guys, this is the resin, and then the C via like the O and O, single and O, bam, right? Gets attached here, and then we have like your obviously have an alpha carbon, you have your H. And then you have your whatever R group. I'm just gonna put this shit here. right? And then you have your amino H3. This is positive. Wait. This is right. So basically, what it's saying is resin is here, exposing this amino group for us to get reacted with. And then what's the next step? So cleavage of the end. Alright, okay. Also, what is this music, bro? Like, this is not the kind of vibe I want. Epidemic sound. You guys are on a timeout for now. Cleavage of the end alpha protecting group, washing step. Okay, as the growing chain is bound to insoluble support, the excess of reagents and soluble byproducts can be removed by filtration. Right? Okay, cool. I don't think this is where. No, this is not where we are. This is not where we were. No. This is not where we were. So anchored by C terminus to an insoluble polymer is assembled by successive addition of protected amino acids constituting its sequence. Right, okay. So like if we're to come here. Oh, I see. So now any new amino acid that you'd want to add is gonna have this exposed, right? So what's gonna happen is like whatever is here, let's say it's F mark. F mark, right? Let's see this is F mark. Let's select O. And then this is the C, obviously then the alpha carbon, H, and then have N, H, 2, and then you have the R. It's basically an N to C addition, right? Okay, we have the first amino acid. We remove this F mark, attach it to the resin, and then we then expose this amino group for the next amino acid, which will have this amino group like blocked and whatever like that, this species on this R group blocked by like by a block or a tridome. And then we take this F mark, we if you were to ask me, I would say we would protonate this, have this pop off, have this react here, and then continue the addition, right? Right? Okay, so let's see. The cleavage of the N-alpha protected group, washing step. Coupling alpha protected amino acid, washing step. So cleavage of the N-alpha protecting group. So I'm just gonna say like there's a P G No, it doesn't make any sense. No, it doesn't make any sense. It doesn't make any sense. Oh, actually, wait, no, it does make sense. It doesn't make sense. It doesn't make sense. It doesn't make sense. It doesn't make sense. It makes sense actually, right? Because if you think about it, if this is always protected, what's gonna happen is when you attach this guy, you then cleave the protecting group here, and then you also remove the F mark here, add them, and then this is blocked off obviously because there's a tridome embark on it. This is also going to be blocked off, and we just have like the amino group still protected. Wow. So on a very, very rough level, I think we're starting to see how this works, right? It's like you have the resin, you have your carboxylate group. You cleave that protecting group there, attach it to the resin. You don't do anything to like. Oh no, actually. Then in the next step, when you want to add a new amino acid, what you're gonna do is you're gonna cleave the protecting group here. Protonate is gonna get it out. Like so, cleave, wash it. So this guy is exposed, but this guy here isn't exposed because like he wasn't in that specific like cleavage step. And then let's see. Copying another protected amino acid, right? So you remove this F mark, attach it here, extend the chain, and this is protected. So basically you only deprotect when you want to add a new residue, right? That's what it sounds like. That's what it sounds like. All right. So you only deprotect when you want to add a new, leaving group. Right. Okay. Alright. As the growth chain is bound to an insoluble support, the excess of reagents and soluble byproducts can be removed by simple filtration. Cool. Washing steps with appropriate solvents ensure the complete removal of cleavage agents after the deprotection step. Yes, that makes sense because once you're done deprotecting, you don't want any more cleavage agents to come here and deprotect this guy before you add it, right? So like you deprotect, wash, remove this, and then introduce this guy with a removed F mark. Yes. Washing steps with appropriate solvents ensure the complete removal of the agents after the deprotection step, control the elimination of excess reagents and byproducts resulting from the coupling step. But general scheme of SPPS, let's see. Alright, so HXP, linker. HX, so okay. I just need to know this one. Yeah, never mind. Either way, you're gonna use context clues. So let's assume like the linker is a resin. Right, okay. So OH, linker, P. Where P, okay, polymer supports. Company of TPG, temporary protecting group. I hate when they like introduce a new language mid-diagram and it's like you have to just continually be referencing it or whatever. TPGAA. Amino acid. So you introduce the amino acid that has a temporary protecting group. So basically, this is your. So let's assume this is your like resin structure, right? This is the binding sites where the first amino acid will get attached to. Let's make that assumption. All right. Boom. Okay. So here, this is going to be connected by. This is gonna be connected by like what you call it? I think a carboxylate, right? I mean, the incoming amino acid is gonna be protected by carboxylate. Okay, cool. So this amino acid then joins in, attached to the C-terminus here, has a temporary protected group on that amine for the amino acid, and then like a protecting group for. I want to assume this is the protecting group for the what you call it, the body, or maybe not actually, maybe not. Actually, let's assume it is. But maybe so that, like for instance, in history, it could be like the tritol, right? So let's assume that's the case. Then, when we want to add a new amino acid, we take this temporary protecting group off, so we cleave it off. We then wash. Remember, we wash the reaction so that we don't have any more TK solution in there, and then we have this exposed sites for an incoming amino acid to bind with their own respective protecting groups, and then we repeat and repeat and repeat and repeat and repeat. So by the time we're done, there's probably gonna, there should be like a. So by the time we're done, I would assume there should be like a protecting group here, like a temporary protecting group here, right? And then with this temporary protecting group, we then cleave it. Or maybe you can just like cleave it in the final step. Maybe we can just cleave it in the final step because all these are protected anyway. So let's assume we cleave this in the final step. And then, voila, like we've made our peptide, still attached to the C-terminus one, very first compound here, very first residue here to the resin. And then we do global deprotection, which is when we then take like our trifluoroacetic acid, our trifluorosilane, and then water mixture cocktail, like a 95, 2.5, 2.5 ratio mix, right? Take that, toss like your resin, your attached peptide into the cocktail. We'll toss the cocktail onto the resin attached peptides. Have you do global deprotection where we not only remove the linker and the resin here, right? We also remove the protecting groups, so like the bark, tritol, and other stuff, right? And other groups. And then once we're done, we have our peptide. So recap, right? We do this, attach here. When we want to add actually, let's not assume what we want to add. We want to prepare this site for the next addition of residue. We cleave the TPG. TPG gets yeeted out, and then this is exposed, right? And then we then wash so that we get rid of any cleavage solvent, so it doesn't like cleave this guy. And once the wash is done, we then bring in this residue, get rid of the F mark, just put in this guy, get rid of the negative reactive, right? And then attach it. Actually, what's the mechanism for this definition? Let's see. NH3 plus. Obviously, like this is gonna be like protonate this guy. It's gonna be negative. Whoa, what did I draw? Actually, this diagram is so wrong. Holy shit. This diagram is so wrong. This is supposed to be like to the carbon, not. Okay, alright. Let's assume this is the carbon, right? Holy shit, that diagram was so fucking wrong. Alright, we heat this guy up. This becomes negative. Comes here, binds to this guy. We heat this guy. So this guy positively charged, right? We come here. Oh my gosh, why am I forgetting my chemistry basics? Oh my gosh. Okay. This guy being positively charged with excess of hydrogens needs to lose one hydrogen to remain in neutral state. This guy is going to be negatively charged, right? So like sigma negative, sigma minus sign here. This guy attacks the nitrogen. Alright? No. We need to make this a good leaving group. Alright, so hydrogen here. This guy gets out. This is now very, very like negative, right? We then come here with like our OH. And then we come here. Right? We have to be negative. Gosh. am I not getting this right now? Oh my god, why is my brain not working right now? I know this stuff is very, very easy. I mean, I haven't even gone into the meat of the whole thing anyway, but yeah, alright. Okay, bar F mark. This is like for protecting the thread. Okay, cool. Blah, 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 blah. Okay. Classical. Oh yeah, this is French. This is definitely French. Look at the French apostrophe. But I know because I changed my phone to French, and then I got these like weird double bracket apostrophe symbols. Anyway, but honestly, like we're running out of time. I'm just gonna like speed on this stuff. Alright, the classical reactor for SPPS consists of a cylindrical vessel, yes, with a fritted disc, yes, we also know that, and a removable lid equipped with a mechanical stirrer. I mean, it is removable on the gyros like protein synthesizer, in the sense that like you have a cap that is movable and basically like you have a seal that moves into the vessel. So I guess that's the removable lid. The resin may also be stirred by bubbling nitrogen through. However, more elaborate equipment is required. Nice, we know that. Rapid small-scale synthesis, a small fritted glass funnel is sufficient. Oxygen and motion need not be strictly excluded. But the cleavage of N-alpha protecting nutrient will form under a hood as the word exposure to piperidine. So, piperidine does a cleavage. So piperidine does the cleavage of this guy. Yes. So piperidine. Actually, I'm gonna say like 40%. This is 40% piperidine, guys. I don't know what you guys have seen here, but this is 40% piperidine. I'm terrible with mouse writing. Alright. 40% piperidine solution, use that to properly cleave a temporary protecting amine. Right? Nice. And what is the structure of piperidine? This is it? Are you kidding me? Bro, this is so underwhelming. Are we dead ass? No. Okay, so it's 4-methylpiperidine. But I mean, even though it's still on. So like what we use in our lab is 4-methylpiperidine, but even though it's still underwhelming, bro. Like, are we dead ass? Like 1, 2, 3, 4. Methylpiperidine. This is so underwhelming. How easy this stuff is, and I don't know it. It's ridiculous. Alright. Okay. Damn, that's low-key kind of bump. Wait, so like, what's special information? Title and summary. Piperidine appears as a colorless liquid with a pepper-like odor. Yes, less dense than water, but will float on water. Flash point is it's an azacycloalkane that is a cyclohexane in which one of the carbons is replaced by nitrogen. And it is a metabolite of cadaverine. Bro. Polyamine found in human intestines. Wow. So smart. Cadaverine found in human intestines. This is actually killing me. It has a role as a base. The reagents. Okay, so it's a base. A base that attacks this user base to attack this protecting group here. A reagent, a catalyst, and I'm still like, I honestly like, bro. If you ask me, this maybe like I am a proponent for honestly strict. So here's one of my like things, right? Like I feel like when we're talking about a compound on material that's open to the public, please let us use the IU pack nomenclature. All right. I mean, I guess cadaverine is simpler, but honestly, like I would always prefer the IU pack nomenclature. That way, it's literally easy for me to construct in my head. You know what I mean? I don't know if there's an IU pack nomenclature for this, but like I can read it and I can decode it in my head mentally. Cadaverine, what am I supposed to infer from this? Like now I have to click on that to look at the structure. I don't know why we're doing this. I see, bro, like cyclopens in me like would have made so much more sense than cadaverine, bro. Cadaverine found in the human, bro. Get out of here. Okay, it's protic. All right. Okay, alright, either way. So, 4-methylpiperidine comes in here, our base, which attacks the protecting group and wraps it and gets heated out and prepares this like site for addition, right? And then what happens is after we've cleaved the piperidine, we wash out the piperidine, right? So remember, attach the resin by the carboxylate group. If we're about to add something, well, actually, technically, it's not even if we're about to add something in anyway. Just like cleave the protecting group from that resin, from that amino group using like 40% piperidine, methyl piperidine. In my case. I don't know how y'all do it. You guys know, right? So cleave with 40% methyl piperidine, and then we wash that out. So that, and the reason we're washing that out is because we don't want to have methyl piperidine inside our reaction vessel when we're then adding the new peptide, because then what will happen is the methylpiperidine will then react with the amino group on that new amino acid that you're trying to introduce to add, right? And then you're just going to cleave it again, and then you can just have all these weird like side reactions going on. Right? It's not what we want. It's not what we want at all. Actually, there's definitely like a better answer to explanation for that, but anyway, this is a rough overview. It's a rough overview. Alright. Okay, alright, so, where were we? F-mark cleavage, or see it. F-mark cleavage. Is the F-mark on the amino carboxylate? Oh, now you want to give me a summary? Man, get out. We keep coming up. Oh, F mark is on the nitrogen. T-butyl. Is that what the temporary protecting group is? Is the C-terminal is even protected? Because that just changed, like, that assumption has been underpinning a lot of my rationalization so far. It's deprotected. Okay, what are we deprotect? Bro, don't piss me off. Do not piss me off. Do not piss me off. C-terminal, okay, so peptide, blah, blah, blah. Okay, what is this? What is this? Genuinely, what is this? Maybe it's the temporary protecting group. Anyway, bro, like, okay. So we remove this temporary group, then come here, do F-mark deprotection with 40% methyl piperidine, right? And then once we have this amount of protection done, we wash away that protection solvent so that we don't accidentally protect the incoming residue. Remove the antimicron residue with. Oh, wait. It is the purpose of HCTU in SPS to activate the C-terminus of the incoming residue. I'm just gonna ask perplexity at this point, but like. I am so prepared to like terminate this tab if it embarrasses me. I don't even know how quick I am, bro. Easy. Nice. Nope. No, in SPPS, is company used to activate incoming F-mark protected amino acid and promote amide bond formation, not specifically to activate the C-terminus of the incoming residue instead of exposing the C-terminal group for reaction. It facilitates activation of the carboxyl group of the incoming amino acid to react with the amine on the growing peptide on the resin. So what is it? So it facilitates activation of the carboxyl group of Is that not what I just fucking said? To activate the C-terminus of the incoming residue. It facilitates activation. I mean, well, even though like tomato, okay, that's not how it is in science. Let me shut up. It's never tomato. It's apples and oranges. Every single time. Okay. It facilitates activation of the carboxyl group of the incoming amino acid to react with the amine on the growing peptide resin. Okay. Enabling coupling under mild conditions and rapid reaction times. Alright? It's a uranium type. It's a uranium type coupling reagent commonly used in bases like DPA and DMF, FMOC SPPS, FMOC SPPS. It activates the carboxyl. Bro, am I like. This is exactly what I said. I literally asked. I'm saying no, but yes. What, bro? This is why I can never really trust AI when you're studying, man. Like you can never. I literally said, it's the purpose of HCTU and SPPS to activate the C-terminus of the incoming residue. Short answer, no. Oh, you know what it also does? It activates the carboxyl group of the incoming amino acid. So the C-terminus. Anyway. So it can form the peptide bond with the N-terminal on the road. Yeah, that's what I'm asking. Alright. Okay, alright. I think we've hit the crux of the matter about our study here so far. We're still gonna finish that whole site, right? So the C-terminus of the green peptide is effectively the resin-bound end. Yes. The coupling step adds the next amino acid to that terminus via an amide bond. Yes. HCTU's role is to convert the carboxyl group into a more reactive ester intermediate, not to unmask or modify a free C-terminus of the ink. Obviously, I'm not talking about nuking the entire oxygen bonds. It's oh my god, bro. Oh my god, I don't like AI sometimes. They think I'm stupid. I think they think I'm stupid, yo. Like, I know I'm stupid to a certain extent, but like, come on, like, let's infer some certain things in the context. Well, whatever. But I guess AI is meant to think that I'm dumb unless proven otherwise. So it's cool, especially if I can chat with no history and no recollection of my past questions and questioning style, right? All right, we only have a couple more searches before this thing is gonna force the sign in. I don't want to do that, so you guys don't see my email. Decline optional. Nope. HCTU and DPA work to While we're at it, let's actually see like oh, DPA by the way is diisopropylethylamine. Let's keep that in our heads. Alright, so HCTU, I mean, not too complex of a structure, and alright, DPA, diisopropylethylamine. Alright, boom. Die. But you guys can reason about this, right? Like diisopropyl. So like isopropyl basically means like when you have propyl or pure like pro anything, just know it has like three carbons in it, right? So like 1, 2, 3. Isopropyl means that whatever is connected to like connected to like the propyl group is in the central carbon. So isopropyl 1, 2, 3, and connected in the middle. That's in the middle. Diisopropyl, we just have 2 isopropyls. Ethyl. This is an ethyl because you don't want 2 ethyl. So diisopropyl ethyl amine because and it's an amine because of the nitrogen. Very rough way to think about these things, but yeah. Alright, cool. Let's go back to complexity. HCTU and DPA working together to turn the incoming amino acid. Whatever. HCTU activates the carboxylic acid of the incoming protected amino acid, forming a reactive species. Okay, cool. DPA deprotonates the amino group. Ah, I see. It deprotonates the amino group. Okay, so it was NH3 plus, just deprotonates that. Yes. Wait, no. NH2 plus, NH2, then NH minus. Anything more? No. NH3 plus, deprotonated, remove that hydrogen, boom. NH2, stable, signal positive, with a negative ester reactive species coming into a bind, and then right. Okay, so basically what's gonna happen is like this guy, HCTU, get the shit out, make this stuff negative. DPA, take away this NH3 plus here, and make it NH2 plus with a signal positive. So this big positive plus a signal positive, and then negative, signal positive, boom. There's the reaction. Alright. Let's well, fuck, let's get there. I'll put that right. Alright. Okay, so then the resin has taken into consideration. I do not care. Blah, blah, blah. I already know much about this. Solvents are filtered up by suction. Okay, cool. Continuous photosynthesis. Now my stick, fully automated SPPS. Yes, this is what we do. This is what we do in a lab. We do not manually do all this stuff. We just have computers that allow us to program the reaction for like n number of residues in the sequence, right? For the entire sequence, no matter how long it is. For n length. For a sequence of n of length n. Oh shit. Put that on. Anyway, large scale photosynthesis, blah 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 blah. Resins. Okay, linkers are bifunctional molecules anchoring the growing peptide. So what is the between the resin and the linker? Oh. Alright. I'm just gonna do this. I think it's gonna be my last question. What is the difference between the resin and the linker in SBS? Please do not. Oh, come on. Alright. It's okay. Alright. And it's okay. Chat. Open. Perplexity. Oh! Are they selling cookies on my thing? Are they selling cookies on my thing? Anyway, whatever, okay. Okay, like, I just need to do this last one. Chat. Back open. Yeah, no. Alright. Cool. You're not telling me now. But, bro. No. I mean, yeah, I guess allowed. Okay, so related but distinct, right? The resin's job is to provide an insoluble support. The linker is the chemical group attached to the resin that connect. Ah, okay, so like support and then the actual stuff, because like the amino acid cannot just bind to the support itself. Okay. So the thing about the linkers are basically so we can assume that linker can be likened to yes, very important here. The loading of resin is essentially a measure of how many reactive linker sites are present. Oh, okay. Oh my gosh, like, okay. Well, thank God I actually streamed this on YouTube, because I'm just gonna come back and like rewatch your stuff. This is amazing. Like, this is amazing. Like, Ultimate Notes app, bro. Because I need to come back and definitely like revisit this in the lab. Right? So the loading of resin is essentially a measure of how many reactive linker sites are present per gram of resin. Reported in moles per grams of resin, moles of linker, millimoles of linker per gram of resin. So 0.2 millimolar loading is like this. 0.2 millimolar of peptide chains can be grown per gram. Okay. So this is what it means. So 0.2 millimoles of linker per gram means that we can grow 0.2 millimoles of peptide chains. Alright, and then same thing for this. So if I rate amide resin with 0.7 millimole per gram, that means there is approximately 0.7 millimole of linker sites available for attaching the amino acid. Nice. Which makes sense why, like, if you choose something with a very, very high loading, you're more like, and you have like less material, more likely to have like a reaction that's going to be sufficient, because there's too many sites to bind, and if you have less material, like geometrically, it's not going to be enough, right? Like for you to what you call it. Not that you're just going to have too many sites to bind. It's like there's some sites exposed while your peptide chain is growing and not fully consumed. You can then have like other like amino acids come in there and then bind to those sites to start your own chains, and then maybe when you go down to take a crude multi-spectrum, you can then see like those residues. You can see like those residues, right? Being cleaved out as well. Like you end up being confused, like, oh, what is this? You just had a very high loading, and then because like you had a very high loading and not enough material, you ultimately, yes, you may have grown like a few peptide chains, but you could like some other unwanted chains. So I guess that makes sense. Alright, but the analogy breaks down. The linker itself is a specific chemical structure. Okay, boom, blah, whatever, ring, wine, 2CC, whatever. The loading is the density of those linkers on the resin. Yeah, alright, cool. Yeah, cool. Alright, nice. Let's see, anything else we need to read in here that is not a product placement information? Linkers, we don't care. Linkers are by functional molecules anchoring the grain pepper to its solid recovery. Alright, linkers are, we measure like linker amounts as loading, basically. Alright, what other techniques are used to synthesize peptides? LPPS. bro, I don't even want to go into this because like this is just gonna get me nervous tonight. All right, and we're done. Whew. All right. So what was the goal again? All right. The goal was what the fuck does HCTU do in peptide synthesis? And now we do realize that HCTU basically, compared to any common carboxylate group, compared to any common so that's the diagram. Compared to any common carboxylate group, by getting rid of the F mark, right? HCTU heats this F mark out, and then deprotonates this NH3 deprotonates this amine, so that by the time by the time HCTU has activated this guy, and it's let's say negative charge, and it's like just a single positive, it favors a reaction in this direction to bind, and it's extending the chain. But I don't think that's what it means by pre. So let me ask. So then, what is pre-activation? So then, what's activated coming before it is added to the resin bound peptide? All right. So you have the F mark on with the coupling. Okay, so without pre-activation, you have your incoming amino acid with the F mark still on it. The coupling reagent, HCTU, your coupling reagent, HCTU, base, dipia, for deprotecting the hydrogen on the amine group on the resin, on the free amine group on the resin. And then resin bound peptide, yeah, all at the same time. Okay, the activated species forms in situ. Well, the amino acid is already competing with other reactions. So let's unpack this. The activated species, which is the carboxylate species right here. So the activated species, right, forms in situ while the amino acid is already competing with other reactions. Are you talking about like the amino acid here? Like, are they saying like while we're forming this is competing with other reactions? Is that what they're saying? No, I don't think this is what they're saying. So he makes this F mark, this HCT whatever plus DPA for a short time, often a few minutes, seconds, minutes. Activated ester or OAT ester or OBT ester. Okay, and then you add that activated to the resin. That activated come out to the resin. F mark A8, right? Activated amino acid. Resin bound amine attacks. Okay. Resin bound amine attacks. Oh, it's reactive. Oh, this is with reactivation. So without reactivation, you add this all at the same time. And if this is also, I mean, this is definitely me like just glossing over this, but like I need to run to work anyway. So let's see. Cover this in the lab. Yeah, actually we'll read a proper paper on it to clean more of this. But yeah, it makes sense. And they will actually study like the mechanism. So the next thing to do will be study the mechanisms of this reaction. Makes sense. Makes a lot of sense. And yeah, y'all. Daniel's gotta go. Thank y'all. I mean, does anyone even see this stuff? But anyway, thank you guys for staying with me. And yeah, we'll see each other some other time. Gotta go to work right now. But alright, peace out. I think now we know what HCTU kind of does, right? Like again, it's just for the activation of the carboxylate on the incoming residue. And then DPA then deprotonates the amine on the resin bound peptide. DPA deprotonates the amine on the growing resin. Yes. On the growing peptide that is already attached to the resin.